Take a look at this data stream. It's moving fast, plotting new points in real time and reacting to real-world volatility. Trying to forecast tomorrow's values from a sequence this chaotic is one of the hardest challenges in analytics. Standard data science relies on static rows and columns, where order doesn't matter. But sequential data streams break those rules. The value of the data is completely tied to the specific moment it was recorded. Yet hidden inside this messy, singular line are three perfect, mathematically predictable patterns. Separating the true signal from the random noise is the mandatory first step before any machine learning algorithm or forecasting model can successfully do its job. This diagram shows the core equation in action. Every observed series is simply the sum of its trend, seasonality, and residuals. First, we isolate the trend. This top line represents the long-term directional movement of the data, stripped of day-to-day noise. You see this shape when a company grows its user base or when global temperatures shift over decades. Next is seasonality. This middle wave captures the strictly repeating patterns, the behaviors that occur at fixed intervals, whether that cycle is daily, weekly, or yearly. Think of it like a heartbeat on a medical monitor. The rhythm is periodic and highly predictable. Finally, we have the residuals. Once you subtract the trend and the seasonality, what remains is the unpredictable noise. These scattered dots represent the sudden shocks, major system outages, and random anomalies. Understanding this anatomy gives you an immediate advantage. It allows you to look at a drop in metrics and mathematically prove whether it's a systemic operational failure or just a completely normal seasonal dip. Before writing a single line of code, you have to look at the shape of your raw data. That visual inspection tells you which of two decomposition models you need to use. Look at the chart on the left. The seasonal waves stay exactly the same size over time, regardless of how high the baseline trend climbs. When variations stay constant like this, you use an additive model. Now compare that to the right side. Here, the seasonal spikes grow proportionally larger as the baseline trend grows. Retail traffic demonstrates this perfectly. If a mall's baseline attendance grows over 10 years, a 10% holiday spike represents thousands more people than it used to. Because the seasonal effect multiplies with the baseline, you use a multiplicative model. Selecting the wrong model type forces legitimate seasonal data to leak into the residual noise, which ruins the decomposition entirely. To apply this practically, we turn to Python's statsmodels library. The mandatory requirement here is explicitly defining your data's periodicity. If you are analyzing hourly data that repeats daily, you must tell the program your period is 24. The actual execution takes just 3 lines. We import the seasonal decompose function, pass in our dataset, specify that we want an additive model, and set our period to 24. Then we plot the result. This chart is the direct output. The computer takes the raw data at the top and automatically generates the isolated trend, seasonal, and residual subplots directly below it. This classical method is a strong baseline, but it relies on a rigid assumption that the sequence perfectly repeats from year to year and that the world never changes its habits. In reality, human behavior does shift over time, and those shifts force seasonal patterns to change with them. For example, decades ago, peak electricity demand happened in the winter because people needed heating. Today, air conditioning has pushed that seasonal peak into the summer. Classical models struggle with this. When rigid trend lines fail to adopt a sudden real-world shocks, obvious patterns spill over into the residual noise. Analysts call this leakage. To solve this, we upgrade to the STL function, which stands for seasonal and trend decomposition using LOES. By setting the robust parameter to true, the algorithm actively protects the trend line from extreme outliers. Look at the residuals panel on the left. That massive dip and the ringing pattern trailing after it is leakage from the classical model. On the right, the STL method has adapted to the shift, returning the residuals to pure, scattered random noise. Because STL adapts to structural changes and isolates extreme anomalies without breaking the underlying math, it is the industry standard for handling real-world data. In just a few lines of code, you've taken a chaotic dataset and transformed it into clear, structured signals. This programmatic breakdown applies to any sequence generated by a human system, whether managing complex supply chains or predicting hospital capacity during an emergency. You can download the script from the description below and run this on your own datasets right now. Ultimately, decomposing a chaotic signal into its core structural components provides the fundamental language required to accurately predict the future.